Okay, so we started. Oh, we already did some of this, didn't we? We talked about the different shapes, simple and closed, and what a polygon is. Right? Remember yeah, that's right. We've been over this. What is the definition of a polygon? Generally, what is a polygon in general?
Like a square, and it has straight sides.
How many? Yeah, it's got straight sides. Exactly. Silvino, right?
Yeah.
Silvino, yeah, exactly. Good job. Straight sides, right? Polygon, straight sides, no curves. No curves on the sides. Oh, yeah. All right, so anyway, yeah, straight sides. A polygon, straight sides, no curves, and also simple and closed. So we've been over that. Let's go forward. And we got right to here. These are a bunch of the polygons. Polygon just means, poly just means many when it's in front of a word. So polygon just means many sides. So there's 3 sides. It's called a triangle, as you know. Quadrilateral, 4 sides. Pentagon, 5 sides. Hexagon, 6 sides, etc. And you don't have to memorize those. You know, you get a 3x5 card for the exams, right? Right. Anything you want, front and back of a 3x5 card. So you don't need to memorize all that stuff. Regular polygon, I think this is right where we got to last time. Obviously, there's writing on it. Regular, I always think that's the wrong word. They should have said perfect, because that's what it really is. A regular polygon is a perfect polygon, meaning all the sides and angles are the same. So here's a regular 5-sided, meaning perfect 5-sided. And here's a regular 6-sided, which means perfect 6-sided shape. Here's a regular 3-sided, and what do we more commonly call that? It's a triangle. What kind of a triangle is that when it's perfect like that? Yeah, do you remember that word? We'll be going over that in a little bit, but you might already remember it. Equilateral. Yeah, equilateral. In other words, it's a regular. Regular, again, means perfect. I think they used the wrong word. But regular triangle or regular... Yeah, what's a regular 4-sided object called?
Square.
Yeah, we more commonly call it a square. You could call it a regular quadrilateral, because quad means 4, right? Quadrilateral. So it's a regular quadrilateral, but nobody would recognize it by that name, right? It's a square is how we commonly say it, but it is also a regular quadrilateral, perfect 4-sided shape. All right. So we'll do more with that, especially Wednesday and Friday. Let's get into let's hone in on triangles a little bit more. Triangle containing one right angle. Again, you can write down some of the stuff on the board, or you don't need to. I mean, you can write down whatever you want. It'll all be on YouTube, so you don't have to. You can always refer back to this, and it's in your notes. I sent you all the PDF notes as well. That's right. So you have that. So a triangle containing one right angle is a right triangle. So a right triangle when it has one right angle. An acute triangle, I say that because I'm probably going to move over this too fast to write it all down, but you have it. An acute triangle just means all the angles are less than 90. Remember, acute angles are less than 90? So an acute triangle, all the angles are less than 90. An obtuse triangle, remember obtuse means more than 90. So that means it has an angle that's bigger than a right angle, bigger than 90. And a scalene, that might be a new one for you. Scalene means the 3 sides are different. So I did put that one on the board, just because that one's probably more valuable. So scalene, all 3 sides are different. So a scalene triangle, all 3 sides are different. Isosceles triangle. Isosceles. What's an isosceles triangle? Yeah. Normally I just think exactly. I just think, well, two equal sides. But actually, notice the definition. They're going to push us on this on the hardest homework problem in this section. I think it's number 10, and the one we'll spend the most time on. They're going to push us pretty hard. It's a pretty tough question. On these, notice it doesn't just say 2 equal sides, does it? It says at least 2 congruent. Congruent is geometry's word for equal. I thought I wrote that. Oh, yeah, there it is. So congruent is a fancy word for equal. They'll use it all semester. Congruent's just a fancy word for equal or same. So 2, I always think 2 equal sides, but they're saying isosceles is 2 or more, right? At least 2 or more. So let me see if there's a good way I can summarize. I have to go quickly through the lecture notes. There. Yeah, let me summarize this for you. So isosceles Here's the way you want to think about it. An isosceles triangle, really there's two cases. It means case 1, 2 equal sides. So that'd be a triangle kind of like this, where this side and this side match. Right? Or case 2, 3 equal sides. Equilateral. In other words, equilateral is a subcase of isosceles. It's a perfect isosceles. Equilateral. Is that making sense? Equilateral is a perfect isosceles because isosceles means 2 or more equal sides. That's the definition they gave. At least 2. You write that. 2 or more equal sides. So you can have 2 equal sides or you can have 3 equal sides, what we more commonly call equilateral. Is that making sense? That's the tricky part. So let's get back to it. We have to remember that. They're going to use that. All right, so where were we? Here, yeah. So going forward then, and then there's equilateral. Equilateral means all 3 sides are equal. And then coming down, now we're on to trapezoid. A trapezoid has, again, they're using the word at least. That's pretty tricky of them. At least one pair of parallel sides. So that means, see how the top and the bottom are parallel, but the right and the left are not? But it says at least. It says at least. So again, let me just go back over here and say that in a way that'll stick with you better, I think. So what they're saying, if I was going to summarize this, is a trapezoid. Trapezoid has one or two parallel sides. Because at least one pair means one or more, right? 1 or 2. So in other words, it's just like the isosceles equilateral thing. You could have case 1 where you have the top and the bottom are equal. Or not equal, sorry, top and bottom are parallel. Top and bottom parallel. Or you could have case 2 where you have top, bottom, and right, left are parallel. Does everybody see that? And what's that more commonly called where both pair of opposite sides are parallel? Parallelogram. Yeah, parallelogram. Because everything's parallel. Yeah, so in other words, a parallelogram is a perfect case of a trapezoid, just like an equilateral triangle is a perfect case of isosceles. Are you tracking with me on that? So it's kind of like we have you could say, hey, let's talk about dogs. And I could say, you have poodles and you have German shepherds. Right? And those are different kind of dogs. Well, that's what we're talking about. We have the category of isosceles triangles, and one kind is where they just have 2 equal sides, and another kind is where they have all 3 sides equal, called equilateral. So equilateral is the perfect case of isosceles. It's a type of isosceles. And parallelogram is the perfect case of trapezoid. Because trapezoid, one pair is parallel or more. So parallelogram, they're both parallel. That's what we're talking about. So that gets a little tricky there. Let me just continue to give the definitions here. Then we talk about a kite. I'll write that up here for you. A kite is just like what you're used to seeing. So if I drew a kite here. So we have these two are congruent. When we put those marks, that means equal length. Are you used to that in geometry? We'll be doing that all semester. Put the single marks through those sides. We're saying those two sides are same length. And then if I put double mark, then I'm saying those other two are the same length, but they're not the same as the top two. because they have double mark instead of single mark. So a kite has two pair of adjacent means next to each other, adjacent sides are congruent, or same, I'll just say same. Same length. Congruent, well, I'll use the geometry word, congruent. Okay. Yeah, so that should say two pair of adjacent sides next to each other are congruent. So you got to have, that's a kite, definition of a kite. And then we have a rhombus coming on down. Let me give you that. So a rhombus has four equal congruent sides. Four equal sides. There's case one where angles are not 90 degrees. Then, so it looked like a diamond basically. Well, here, let me do it a little bit better. Like that. So there we go. And case two, angles are 90 degrees. So what do we call that? When the four sides are all equal in a rhombus. These are both rhombuses. But the bottom one, number two, case two, is more commonly called what? It's a square. So I want you to see how certain shapes are subcategories of other shapes. That's what's tricky. That's what's going to be really tricky, and I think it's number 10 when we get to it, because they're going to really push us pretty hard on all these relationships. So a square is a type of rhombus. It's a perfect rhombus, where all the angles are 90 degrees. So a rhombus is four equal sides. The angles may or may not be all the same. If they are, it's a square, but it's still a rhombus. By the way, notice square fits almost every category. A square is a kite, too. He's a perfect kite, right? What do you got to be to a kite? Two pair of adjacent sides. Well, square has all four sides the same. So yeah, he's a kite. Square is a perfect kite, isn't he? So that's the kind of thing they're going to push us on, which is going to be tricky when we get to that question, is how these connect with each other. It's a good exercise in logic and definitions, and that's what engineers do. You're going to be training future engineers, and that's how they fit things together. So it's good practice on that logic, shape thinking. All right, I think we have, what else do we get? Did we get most of the definitions, I think? Let's go back here. Kite, isosceles. I'm not going to write down isosceles trapezoid. That one's obvious, I think. Isosceles trapezoid. Isosceles means two equal sides, or two things that are equal, right? Two sides or two angles, same thing. Isosceles trapezoid just has two equal angles. I think that's obvious. Parallelogram, rectangle. You know a rectangle. Rhombus, square. Yeah. So we got them all. So. All right, so I just want to give you an example from an elementary school book. They do that every now and then, which is helpful just to see. We're not going to solve these problems, but I just want you to see. I know they're too small to solve, but it's basically showing us the beginning of symmetry. We're about to dive into symmetry right now. So it's giving us different shapes here with lines through them, lines of symmetry. This is stuff we're about to do, is stuff that's actually in the curriculum you will teach. So let's go through some definitions. Turn rotational symmetries. So we're talking about turn or rotational symmetries. Now we have that whole formal definition. Let me just make it simpler. Turn symmetry, what it means, actually I didn't need to write the word again. It means any angles less than 360. Well, I'm not saying that very well. Let me try again. Turn the object some angle some angle and it goes back upon itself. So just to put it in simple talk, so turn an object some angle and it goes back upon itself. And that angle must be less than 360. So let me give you an example. Suppose if I have a square. Sorry, my drawing is not the best. There we go. Let's just start. I know they have examples there from other ones, but let's just talk about a square. What if you take a square and you put a dot right in the center and you start to rotate that square, you start to turn that square? How far, what angle do you need to turn it through so that it'll come right back on itself? How far do I rotate it before it fits back on itself? Yeah, so if it helps, just put a line in there straight up. So if I turn that straight up like a clock, right? Say it's straight up and I'm going to go, whatever, I'll go this way. How far does this need to go? Well, until that goes right there, then it'll be back onto itself, won't it? Can you picture that? Right? If I was to grab this square, and start turning it, and then click, it would be right back on itself, wouldn't it? How far did I turn there? 90 degrees, right? If I turn 90 degrees, it'll be right back on itself. So we would say it has 90-degree turn symmetry. Symmetry means same. Whenever sim is in front of a word, it means same. So it'll look the same. It'll fit right back onto itself, the same, won't it? If you turn it 90 degrees about its center. But not just 90, huh? We could turn it another 90 until that comes down to there. So how far altogether is that? 180. It also has 180, and not just that. We could turn it another 90. You're getting it, I'm sure. So how far would that be? 270. And not just that, all the way back until it's all the way around, right? All the way around 360. But we don't want to list that. That's why we're saying here. I want to show you why we say that. Of course, any object you turn all the way around will be back onto itself. We don't want to bother to list that. That's obviously true always. We don't care about that. Makes sense why we're not listing the 360? Any object you turn all the way around, of course it's back onto itself. We're saying is there some angle less than 360, less than all the way around, that you can turn it and it'll be back onto itself. Yeah, for a square, 90, 180, or 270 will all work. It has those turn symmetries or rotation symmetries. Comments or questions? Is making sense? All right, and then point symmetry, simply put, if you have rotation, put it this way, turn symmetry equal to 180. That's it. All those fancy words. They could just say that. I don't know what they're saying in this whole thing, but that's it. Basically, if any shape that you could turn halfway around, 180, right? Like you do a 180 in your car, you make a U-turn. That's a 180, right? So any shape that you can turn halfway around and it's back onto itself, that shape has what we call point symmetry, which means it's symmetric about its center point. It's spaced out evenly. Back to the square again. So the square, we know we can, the straight up, we could flip that to straight down. It has 180. It also has 90 and 270, as we saw. It has 180, which means you could turn it halfway around. It'll be back onto itself. And so that means it's symmetric about its center point, is what that means. All right, so simply put, you can have turn symmetry, whatever angle's less than 360 to go back into itself. And if you happen to have the 180, we call that point symmetry because it's symmetric about the center point. And with that, we dive into the homework. So there's the intro. Let's dive into the homework. I'll try to go quickly over the easy ones so I can get to the hard ones and slow down. Is that figure convex or concave? Remember those words? Yeah, this one goes in, so that's concave. So concave means caved in. So if something goes in, it's called concave. It caves in. How about question 2? What type of polygon must have a diagonal such that at least part of the diagonal falls in the exterior of the polygon? That's a bunch of fancy talk. But what they're really saying, remember the formal definition? We can look at this last picture right here, this one right there, and we can just say, oh, that's, it's concave. It caves in there. And that's right. That's, of course, right. The formal way that they say it, the formal geometry definition for concave, they say, I think I mentioned it briefly last time, if you can go from one point to the other straight, and you travel outside the object, exterior to the object, then you're concave. They're just saying, do you know, no, whoop, I did the wrong one. Concave, there we go. Do you know that's the formal definition of concave? If you travel from one point to the other and in a straight line and it goes outside the object must be caved in. That's why the straight line is outside. So that's the formal definition for a concave object. Some straight lines go outside the object. All right. I'm going to move on to 3. Again, if I'm too quick, it'll be on YouTube, but I want to get to the hard ones so I can slow down there. If possible, draw a right scalene triangle. If it is not possible, state why. What's scalene mean again? 3 sides that are different, huh? Yeah. 3 sides that are not the same. Right? 3 sides that are different. So can that be the case? Can you have like a right triangle with 3 different sides? Let's go through it. How about A? Does A fit that situation? No, A's not even in the ballpark of that situation, huh? He's got 2 equal sides. They're supposed to all be different. He doesn't even have a right angle. How about B? I don't know what's up with B, why they're drawing like 2 triangles there. I never have figured that out, but that's not the answer. It's just weird. On to C. So, is C right? Is C a right triangle? Yeah, it's got a right angle there, huh? Is it got 3 sides that are different? Well, I don't know. I don't know that third side. I know 2 of them are different, 9 and 11. But what about that other third side that we don't know? Could that be like 11? Maybe it is, and then it's not scalene. If that's 11, then it's not scalene because it's supposed to be all 3 sides that are different, huh? What do you think? Could that be 11? Or is it some reason that it's impossible for that to be? Does that have to be different than 11? How do we know? Yeah, good memory. Yeah, the little Pythagorean theorem thing. I'm not going to do the formal. We'll do that later. We'll do a lot of it later. But for now, let's just say that third side's got to be the longest side. It's got to be longer than 11. The formal reason you guys are right is Pythagorean theorem, but I'm not going to pull that out right now. We'll do it later. I mean, in a month or something. But we'll just say, hey, yeah, in a right triangle, that other side. Anybody remember the name of the side across from a right triangle? It's got a hypotenuse. Yeah, a lot of you remember. It's longer. The point is, that's got to be longer than 12. So yeah, that's our answer. Those 3 sides have to be different, and it's a right angle. So yeah, that's something bigger than 11. So that's a scalene triangle. All 3 sides are different. It's a right angle. Yeah. All right, on we go. So we got this. Always looks like a cat. To me, anyway. All right. So determine if the figure to the right has, first off, line symmetry. Is there a line that we could draw somewhere on that figure that it's symmetric about that line? Let me put it to you this way. A fold line. So a line of symmetry is a fold line. It's a line about which you could fold the object and it would go right unto itself. A symmetry means same, right? It would be the same on the 2 sides of that line, that fold line. So can you picture a line that you could fold the shape on and it would fit unto itself? Where would that line go? What was that?
I think like right here between.
Yeah, right between the ears, huh?
Yeah.
Exactly, right? And that's right, isn't it? That's the fold line. It would fold right about that line. It would fit right into itself there perfectly. So yes, it has a line of symmetry. How about the second question? Does it have rotational symmetry? Is there some angle we could rotate it and it would go back into itself? I mean, less than all the way around. Of course, we could always do all the way around. We don't count that. Is there something less? Can we turn it? Can we make one of those ears come onto the other and everything will fit? No, it's not going to work. If they'd put like other ears over here, then yeah, but no, they didn't. So no, there's no angles you could turn it. How about, does it have point symmetry? How do you decide point symmetry? Yeah, they're simply asking, does it have half turn, 180, or not? No, because it didn't have any rotational symmetry, so it does not have 180 degrees. So it doesn't have point symmetry, right? That was the test for point symmetry right here. Turn symmetry of 180, that is point symmetry. So there we go. Stop me if you want to talk about it. On to this one we go. So they're giving us that arrow, and they're asking us, A, B, C, or D, which of those has the right symmetry lines? Which is it, C or D? D? How about C? What's wrong with C if you don't like C? Which line's not good on C? Yeah, this is not really a fold line, is it? If you fold it, it wouldn't be onto itself, would it? So yeah, it's only D. It's only that line through the middle, isn't it? That's the only fold line for that shape. All right, now this one gets a little more interesting. We'll start to slow down a little bit. So part A, which figure below has one line of symmetry but no rotational symmetry? So this line of symmetry, and you can't rotate it, right? If you turned it, it's not going to be back onto itself unless you turned it all the way around. Yeah, good job. Good job. That good? What's wrong with A? Why is A not the answer there? Yeah, you could rotate it, huh? Yeah, you could turn A halfway around and be back into itself, wouldn't it? Yeah, and plus it has lines of symmetry, doesn't it? Two of them. It's supposed to only have one. Yeah, A's got a problem. B, what's wrong with B? Why is B not the answer? How many lines of symmetry does B have? Yeah, through any of the vertices. Those are all fold lines, aren't they? Right, it's got three of those. What's his rotation? How far could you rotate that triangle and have it back into itself? Well, we can always do 360, but we want less than 360. Couldn't you turn it 1/3 of the way around? So what's 1/3 of 360? 120? Yeah, we'll talk more about that later. It's clearly you could turn it unto itself. I guess it kind of looks equilateral. Anyway, so on we go. Let's go to part B. Which figure below has rotational symmetry but no line symmetry? C? Is that true? C has, C have rotational? Yeah, you could rotate it 180 degrees. Now you could turn it halfway around and it would be right unto itself again, huh? Has 180 degree rotational, and it has no line symmetry. There's no fold lines for C. Perfect. It is C, isn't it? That good? Comments or questions on that? And then part C, how about this one? Which figure has one line of symmetry and rotational? What do we think? Any answers? So, not possible? So let's go, okay, so it's not possible, let's go through. What's wrong with A? Why is A not the answer then? Let's go case by case. So why is A no good? Two lines, huh? Right down the middle this way or right down the middle that way. Two fold lines that would be unto itself. So it's only supposed to have one line. So it's not A. How about B? What's B's problem? Yeah, he's got the one fold line only, but yeah, you can't rotate him any less than all the way around and have him fit unto himself, huh? Right? So he's got no rotational symmetry. He's supposed to have rotational symmetry. He doesn't. What's wrong with C? What's C's problem? Again, 2 lines, supposed to only have 1 line of symmetry. And D, same thing, 2 lines. So yeah, E, not possible. Not possible. Good work. All right. 7, I think this is simple for you. More symmetry. In fact, I'm just going to move on. That'll be simple for you. 8, same thing. I'm just skipping along. 9, concave, convex. Basically, this figure here, part A, this figure, it comes in just a little bit right there. It's concave. It caves in just a little bit right there. B, also, I think you can see it caves in right there. C does not cave in, so that's convex. D, it's concave right here. It caves in, meaning if you can go from one point to another with a straight line that goes outside the shape, that's concave. It's caved in. I didn't do that very neatly. So you go from here to here, right? And that's concave. Caves in just a little bit. All right, here's where I wanted to hurry and get to. This is a really hard one. This is the hardest question on the thing. Number 10. So let's take a look at number 10. So they're having us mix and match. They're giving us a bunch of pictures and then a bunch of definitions. And we've got the definitions, for parallelogram, isosceles triangle, square, and blah, blah, blah. Rhombus and kite and all that stuff. But what they did, they actually did a really good job. Such a good job. This is a challenging problem. I spent a long time when I did your homework beforehand a couple weeks ago. And I got it wrong at first, so it's pretty tricky. Because they have you, it's not just like match them up one for one. That'd probably be pretty easy. You can use elimination and everything. It's several of them will go in several different categories. Some of them repeating. Some of them won't go in any categories at all. So it's a real tricky mix and match question. It makes us really think carefully about these definitions. So let's dive in. So what's this one first off? So I can't make it any bigger or the words won't fit on there, so I'm going to leave it like this. So anyway, so what's that first one? What kind of shape is that? Yeah, it's a kite, isn't it? That's a kite, right? 2 sides that are congruent. So see how it has. Can you see the single mark, double mark, double mark? So 2 pair of equal sides, that's a kite. Yeah, so that one's easy. That's even K. That worked out so well. It's even the K down there for the kite. You can see it down there at the bottom. K for kite. All right, let's go to the next one. So that one's not hard. The next one, what kind of shape is that? I know it's kind of small. There's double here, single there, single there. What? Yeah, it's a parallelogram, right? And it just seems so easy for us. Like, well, yeah, it's a parallelogram. But then look down at the categories. They don't have a simple parallelogram category. They're making it tricky because they're making us think out these definitions. They have parallelogram but not trapezoid, or trapezoid but not parallelogram. Which one of those is it? Let's go look at the categories. Right there. What's a parallelogram? A perfect trapezoid. It's a special case of a trapezoid, isn't it? It's a perfect trapezoid. So if something's a parallelogram, is it a trapezoid? Yeah, it's a perfect trapezoid. Like maybe a German Shepherd's a perfect dog. I didn't write that out, or whatever your favorite kind of dog is. Right? It fits within the dog category, right? Parallelogram is a kind of trapezoid. It's a perfect trapezoid. Remember, trapezoid can have only the top and the bottom parallel, or it can have top, bottom, and right, left parallel, right? 1 or 2 parallel sides. Parallelogram has 2. It's a kind of trapezoid. It's a perfect trapezoid. So could you be a parallelogram and not be a trapezoid? Could you be a German Shepherd and not be a dog? No. If you're a parallelogram, you are a kind of trapezoid. You're a perfect trapezoid, huh? So let's go back to the categories with that thought in mind. Look at E. Look at category E for a minute. A trapezoid, but not a parallelogram. Look at D. A parallelogram, but not a trapezoid. One of those two is impossible, and we should cross it out. Nothing could do that. Which one? D. You can't be a parallelogram, but not a trapezoid. If you're a parallelogram, you're a perfect trapezoid. Do you see they're trying to... This is what helped me as I finally did the homework problem right. As I said, I'm going to first cross out their bogus categories. They have 3 or 4 bogus categories that nothing will ever fit into. There's the first one. You can't be a parallelogram, but not a trapezoid. If you're a parallelogram, you're a perfect kind of trapezoid. So nothing is going to be put into that category. They're testing us with that category. Does that make sense there? Now, okay, so where does this go then? Does this go in E? Is it a trapezoid, but not a parallelogram? No, it is a parallelogram. And again, you can't go in D because, although it is a parallelogram, it's also a trapezoid. It's both a parallelogram and a trapezoid. It's a parallelogram, which is a perfect kind of trapezoid. So there's no place to put it. Yeah, no place. That's one of those you don't move. So that's why they made this a really hard question. You just leave it be, which is a little disturbing, huh? But that's what we got to do. All right, let's move on to the next one. Next part. What kind of shape is that? Can you see it? It's kind of tiny. They have a mark here and a mark here. So it's an isosceles triangle, right? 2 equal sides. But again, they're going to play games with us with all the category names. So we know it's an isosceles triangle. So, okay, so does it go here? Yeah, for sure. So it goes in category A. We'll put an A there. So K here, A here. But that's not all. It can fit in more than one category, perhaps. Let's look at the next one. Is it also isosceles but not equilateral? Now, what's up with that? Let's go back. Let's look at the categories again. Did I put it here? Yeah. Isosceles means 2 or more equal sides. So you can be 2 equal sides, or you can be all 3 sides equal, which we call equilateral. So again, it's just like the parallelogram is a perfect trapezoid. Equilateral triangle is a perfect isosceles, right? It's a kind of isosceles. It's the dog category, and the German Shepherd is the perfect dog. Or the equilateral triangle is the perfect type of isosceles. Isosceles means 2 or more. So, okay. So let's go back to the question then. So back to this one right here still. Is he isosceles but not equilateral? Yeah. He's also that. A and B for him. He's going to be slid into both categories, isn't he? He's isosceles, but he's not equilateral, right? He has 2 sides, but not 3. And he's also just generally isosceles. A. Good. How about the next one? How about this question? Now, I don't know if you can see it. It has all 3 marks. It's equilateral, right? All the sides, all the angles are equilateral. So where does he go, though? He's equilateral, but which... Oh, so does he go over here? Equilateral, but not isosceles? No, what's that? Another bogus category. Cross this one out, right? If you're equilateral, you are isosceles, right? If you're equilateral, you're the perfect isosceles. You can't do that. That's another bogus category. So anyway, back to the question. Where are we going to put this thing then? Is he going category B? Is he isosceles but not equilateral? No, clearly not. He is equilateral. So is he going category A? Yeah, just A, which seems weird, doesn't it? We can only call him isosceles? Yeah, he's a perfect isosceles is what he is. So see how they're really being pretty tricky on this question. They make us really think carefully about these definitions. All right, next one. What kind of shape is that one? Yeah, that's just a kite, isn't it? I don't know if you can see it. Double here and single marks there. That's the definition of kite again. So that's going to go in K. Let's go on to this one. Rectangle. It even says the name rectangle. We know it's a rectangle, but they're going to play games with the categories again. So what kind of a rectangle category should it go in? Is it a rectangle but not a square? Is that true? Yeah, that's true, huh? So it's F. It's a rectangle but not a square. But hold on. Other categories. Could it be a square but not a rectangle? Can you be a square but not a rectangle? No, I don't know if I put that definition on there, but it's the same thing as those other ones. Let me add it. Yeah, so, or did I? Did I put it there? No, I didn't. Yeah, so a rectangle, case 1 can be like that. Case 2 can be a square. A square is a perfect kind of rectangle, just like all the other ones. So, can you be a square but not be a rectangle? No, that's the perfect rectangle. There's another bogus category. Nothing will go in that category. Can you be a square but not a trapezoid? Is that possible? How are we doing? Are you getting tired of these weird questions? A square but not a trapezoid? What's a trapezoid? Top and bottom are parallel, or maybe all 4 sides are parallel. Is a square a trapezoid? Are the top and the bottom parallel in the square? Are the right and the left parallel? Yeah. A square is a perfect trapezoid. A square is a perfect kite. A square is a perfect rhombus. A square is the perfect 4-sided shape. He fits like almost all those categories. He's the perfect of everybody, isn't he? Right? Square's got it all. Top and bottom are parallel. Right and left are parallel. All 4 sides are the same, like a rhombus. These are the same, like a kite. He's got it all. So you can't be a square but not a trapezoid. That's another bogus category. Those are all bogus. Let's get back to the rectangle now. Rectangle, so where does he go? Is he a rectangle? Yeah, we already did F. Is he anything else? Is he a rhombus but not a kite? Is he a rhombus but not a kite? Is he a rhombus but not a kite? I think that too might be a bogus category. Oh yeah, it is. That can't be, right? Let me cross that out. That's another bogus, because remember what rhombus is? You might be thinking, no, I'm getting completely lost, and I know it's tricky. A rhombus has 4 equal sides. So therefore, it fits the kite. A kite, it's a more specific kind of kite, right? If you have 4 equal sides, then you have at least 2. How we doing? You getting these logical relationships on this? So that one is going to be another bogus category that I crossed off. So is there anything else we can do for rectangle? Is it a rhombus? Yeah, it is. It fits both those categories. It's a rhombus. Rhombus means 4 sides. A rectangle. Oh, no, that's not true. I take it back. It's not. A rhombus has to have all 4 sides equal, doesn't it? Rectangle only has top and bottom and right and left. It's not. It's just F. All right. We are going to have